This is what 24 atmospheres of pressure does to a steel tube carrying 132 people. At 800 feet beneath the surface of the ocean, the hull is groaning. The metal is flexing inward under 353 pounds per square inch of pressure. Inside, the crew is breathing normal air, eating dinner, checking instruments, as if absolutely none of it is happening. That contradiction, the violence outside and the calm inside, is what makes submarines one of the most staggering engineering achievements in history. Today, we are going to walk through exactly what goes on at 800 feet, what the physics are doing to the vessel, what the crew actually feels, how they stay alive, and what happens when any part of it fails. Pressure is where we start, because the numbers are hard to believe. 1 full atmosphere of pressure, about 14.7 pounds per square inch, stacks onto the hull for every 33 feet of descent. That is the same force as the entire weight of the atmosphere above you at sea level, added again and again as the submarine sinks deeper. By 800 feet, roughly 24 of those atmospheres have piled up, enough force to crush most land mammals outright. A standard smartwatch carries a water resistance rating of about 5 atmospheres, around 164 feet, which means 800 feet represents nearly 5 times that pressure. There is a demonstration that gets passed around submarine crews like folklore, except it is real. You tie a piece of string taut across the interior of the submarine while it sits near the surface, then you dive to test depth. When you check the string again, it droops visibly because the walls have moved inward. The even more striking version goes like this: tie the string tight at maximum depth, and it will snap before the submarine reaches the surface. And submarines do not just resist this pressure, they deform under it. The hull physically compresses inward, and we are not talking about some theoretical microscopic flex. Multiple former submariners describe the pressure hull shrinking by several inches in diameter at depth. That flex is by design, and the metal that allows it matters enormously. U.S. submarines rely on high-yield steels designated HY-80 and HY-100. Virginia-class boats, the Navy's current generation of fast-attack submarines, use HY-100 steel in a double-hull configuration. Manufacturing precision is extreme because even a 1-inch deviation from perfect roundness in the hull cuts the maximum load capacity by over 30%. Every weld gets checked multiple times using different methods. At these depths, imperfection kills. The Soviets took a different path during the Cold War. They built titanium hulls, most famously on the Alpha-class submarines and the K-278 Komsomoles, which carried a depth rating of 1,300 meters, over 4,200 feet. Titanium allowed dramatically deeper dives, but it came with trade-offs, enormous cost, and a metal that grew brittle over repeated dive cycles. Steel or titanium, each approach represents a different answer to the same question. How do you build something that can survive being slowly crushed over and over again for decades? So the hull is compressing and groaning under load. What does the crew actually experience at 800 feet? Almost nothing, and that is the entire point. Air pressure inside the submarine stays at roughly normal surface-level atmospheric pressure, right around 14.7 pounds per square inch, regardless of how deep the boat goes. The hull absorbs all of the external force. Physiologically, the crew feels no different than if they were standing on land. Their ears do not pop, their bodies carry no strain. Engineering has transferred the full burden of the deep ocean onto the metal surrounding them. But none of that means 800 feet feels like home. Sound hits you first. Submarine hulls produce creaking, groaning, and popping noises during deep dives as the metal flexes under load. Former submariners describe this consistently. Beyond the hull noise, most of what you hear inside a submarine comes from ventilation fans pushing air through the vessel non-stop. During the dive itself, air forced out of the main ballast tanks creates a much louder rush. Temperature registers next, or more accurately, the effort required to manage it. At 800 feet, the submarine sits well within what oceanographers call the permanent thermocline, the transition layer between warm surface water and cold deep water that extends from roughly 660 feet down to about 3,000 feet. Water temperatures at this depth typically fall between 39 and 50 degrees Fahrenheit, depending on latitude and season. The submarine's metal hull conducts internal heat directly into that cold water, functioning like a massive radiator running in reverse, which means the boat has to be electrically heated just to keep the crew comfortable. All of that power draws from the nuclear reactor. Then comes the stillness. Surface waves rock a submarine on top of the water, but at depth, nothing moves. Only the most violent hurricanes and cyclones produce wave motion reaching as deep as 400 feet. At 800 feet, the water is perfectly still, no rocking, no swaying, just a vessel hanging in motionless silence. And then there is the darkness. Navy submarines carry no windows and no portholes, so the crew cannot see outside. Even if they could, there would be nothing to look at. Sunlight penetrates the ocean to somewhere between 660 and 1,000 feet, depending on water clarity, but it becomes negligible well before 800 feet. Beyond the hull is total, permanent blackness. Picture what that adds up to. You are inside a steel cylinder that is shrinking under pressure, heated artificially, suspended in perfect silence and perfect dark. And you might stay there for months. That brings up the obvious problem. How do you keep 132 people alive inside a sealed metal tube hundreds of feet underwater? The answer runs on some genuinely clever chemistry. A submarine is, stripped down to basics, a sealed container holding people and a finite supply of air. Three things have to happen continuously to keep that air breathable. Oxygen has to be replenished, carbon dioxide has to be removed, and moisture has to be controlled. Oxygen comes from electrolysis, splitting water molecules into hydrogen and oxygen using electric current. But an important step comes before any of that can work. You cannot use the seawater surrounding the submarine directly. Electrolyzing salt water does not produce oxygen, it produces chlorine gas, which is lethal. So the seawater first passes through desalination, either by distillation or reverse osmosis, to produce purified fresh water, and only then does it go through the electrolysis system. Oxygen feeds into the submarine's atmosphere, and the hydrogen byproduct is either vented overboard or eliminated through catalytic burners, depending on the boat's design. Modern U.S. submarines carry systems built by Collins Aerospace, which rely on proton exchange membrane electrolysis. These run automatically and are installed on every operational class of U.S. submarine. Electrolysis equipment can break down, though, and that is where one of the stranger objects on a military vessel comes in. Submariners call them oxygen candles, cylinders packed with sodium chlorate and iron powder. When ignited at temperatures over 600 degrees Celsius, they decompose chemically and release pure oxygen. You are literally burning a candle to create breathable air. It sounds counterintuitive, but it works. Meanwhile, the carbon dioxide the crew exhales gets pulled through chemical scrubbers that trap it before concentrations climb high enough to become harmful. These systems run simultaneously, without stopping. They are the reason a nuclear submarine's endurance limit has nothing to do with air. It comes down to food. Submarines typically stock a 90-day supply, and when that runs out, the boat surfaces. Not because it cannot breathe, but because it cannot eat. And that has happened. On April 10, 1963, the USS Thresher, a different class of submarine carrying a smaller crew of 129, was running deep diving tests about 220 miles east of Cape Cod, Massachusetts. The Thresher was the most advanced nuclear submarine of its era. Below the boat lay 8,400 feet of open water. The escort ship USS Skylark monitored from the surface. At roughly 9:13 that morning, a message reached the Skylark from the Thresher reporting a minor problem. Communication dropped for the next 4 minutes. Then, at 9:17, a final garbled transmission came through, and only 2 words could be made out: test depth. After that, a dull, muffled thud. All 129 crew members and civilian shipyard personnel aboard the Thresher died. The hull had imploded. It remains the worst submarine disaster in U.S. Navy history, and stands as the first nuclear submarine ever lost at sea. Investigators concluded that the most probable cause was a piping system failure, a cracked silver brazed joint in a saltwater cooling system, likely in the engine room. Flooding from the breach shorted critical electrical circuits and killed propulsion power. The crew tried to blow the main ballast tanks to surface, but could not get there in time. The Thresher sank past its test depth of about 1,300 feet, and the hull imploded at an estimated depth near 2,400 feet. An alternative theory published decades later by the Navy's own longtime acoustic analyst pointed to an electrical failure rather than flooding, and that debate has never been fully resolved. What did change, permanently and completely, was the Navy's approach to submarine safety. The Thresher disaster led directly to the creation of SUBSAFE, a quality assurance program that now dictates everything from approved materials to how every weld and mechanical joint must be tested, inspected, and documented in any system whose failure could cause a submarine to sink. In 1988, Vice Admiral Bruce DeMars, the Navy's chief submarine officer, stated that the loss of Thresher initiated fundamental changes in design, construction, inspections, safety checks, and tests across the entire submarine force. 2 days after the sinking, President John F. Kennedy issued Executive Order 11,104, ordering flags across the country lowered to half-staff. $45 million built the Thresher in 1960, about $480 million in today's dollars. A single Virginia-class submarine now costs roughly $2.8 billion, climbing to $3.2 billion for the latest Block 5 variants, carrying the Virginia payload module. Annual operating costs alone run around $50 million per boat. These rank among the most expensive machines ever constructed, and SUBSAFE is a major part of why they cost what they do. And yet, somehow, people volunteered for this. They hot-racked in bunks still warm from the last shift, shared a handful of showers among dozens, filled dead hours with board games and movies, and called it a career. One more piece of this story deserves attention, and it has nothing to do with survival or engineering. It explains why submarines go to 800 feet in the first place. At that depth, a submarine sits inside the permanent thermocline, the zone where water temperature drops rapidly as you descend. What makes that matter has to do with sound. The thermocline creates a gradient in sound speed that can reflect active sonar signals, bending them away from objects below the layer. What that means in practice is straightforward. A submarine that dives below the thermocline becomes far harder to detect with sonar from above. The temperature boundary functions as an acoustic shield. That is one of the core tactical reasons submarines operate at depth. They are not just hiding from sight, they are hiding from sound. At 800 feet, the physics of the ocean itself is working in your favor. Everything about this environment wants to kill the people inside. And everything about the engineering keeps it from succeeding. That tension between the physics that should destroy the vessel and the engineering holding it together defines life at 800 feet. You can hear it in every creak of the hull, every cycle of the oxygen generator, every weld inspected under a program that exists because once the engineering fell short. Every submarine that has dived since carries the answer to that lesson welded into its hull. And somewhere right now, one of them is descending past 800 feet, the surface disappearing above it, until there is nothing left but the dark and the steel and the quiet hum of systems keeping everyone inside alive.